Yes, ladies and gentlemen, with my talk, I would like to introduce the spectroscopic portrait of the binary star, the binary system, Cephei, and emphasize particularly the eclipse that took place from 2017 to 2019. And some of the more recent findings on this binary system resulted from observations in understood astronomy, which underlines, in my opinion, once again, the importance of the collaboration between these both parties. I don't want to use the term pro-M. I prefer to use, since yesterday evening, to use more the term both parties on the same level. Okay. One of the largest and most famous stars in the northern hemisphere, which can be found hidden within a dark interstellar dust cloud, in the constellation Cepheus, is an extraordinary, very good star Cephei, with visual brightness of 4.9 magnitude. And if the interstellar dust cloud didn't darken its light, the visual brightness would be 2.191 magnitude. And this figure here gives only an impression of the enormous difference in size between Cephei, which is the main star of the system, and to our sun, not only one. And Cephei is, in my opinion, an unrivaled example of binary system with a mass exchange in the periastrum between those both components, in which the inflated M2 supergiant with its extended atmosphere is orbited by a much weaker but much hotter main sequence star of the spectral type B. And the B star, with its own radius of approximate 13 solar radii, orbits this large M2 supergiant on an average distance of approximate 90 to 20 astronomical units over a period of 20.4 years, with an orbital eccentricity of 0.35 and an orbital inclination of 76 to 77 degrees, where it's itself surrounded by an extended hydrogen gas disk. And the outer atmospheric layer of this M star, the chromosphere, which is also the acceleration zone of its self-released stellar wind, completely envelopes the orbit of this companion star. Because of the supersonic velocity of this B star, this companion, which moves on its orbit through the M star supergiant's accelerated stellar wind, and because of the associated interaction of this companion, of this B star and its wind, a shock bow occurs in front of the B star with an outflowing gas cone. This one, yes. The H-alpha emission that arises and around the companion star is most likely due to the recombination of ionized hydrogen, since all lines of the so-called Balmer series have similar emissions. And in addition, the neutral hydrogen wind of this supergiant is photoionized around the B star from its extreme ultraviolet spectrum at wavelengths below the 900 angstrom. And these hydrogen ions also recombine, and leading to the radiation cascade of the various Balmer series emission lines. That means that the region around this companion, around the B star, initially a single undisturbed emission. It's produced, which is shown here in this figure, in spectra of the astronomer wide as a dashed line. However, since the entire binary system is surrounded by the large-scale cloud of neutral hydrogen, the stellar wind of the M-star supergiant, it creates a very deep absorption in the observer perspective. That splits the intrinsic single emission into two components, into a blue, so-called V component, and into a red, so-called R component. In theoretical, we would now expect that the high velocity in the wings of the H-alpha profile, up to 300 kilometers per second, of course starting from the center of the line, as well as the similarly high velocities in some ultraviolet emission lines, originate in a gravitationally bound accretion disk, which is in a Kepler rotation around this massive companion, this massive B star. The size of this companion and its accretion disk, which creates the ultraviolet continuum, is very small compared with the M supergiant. And we know this because the ultraviolet light curve drops sharply during and after the eclipsing, suggesting that the ultraviolet continuum, the continuum flux, comes from this small area. And we assume that the gas responsible for the emission is concentrated in the orbital plane of this binary system, and appears as an accretion disk around the B star near this plane, this orbital plane. As a result of the eclipse by this supergiant, the emission lines disappear or reappear afterwards, and the times at which this happens provide information about the location of the origin and shape of the emission itself. And this figure here illustrates only the orbit of the hot companion as it actually projects in the sky, with temporal marks indicating the position of the star, obtained from 21 satellite observations by the astronomers Bennett and Bauer. Yeah, the visible spectral region, of CCD spectra of this system, VV Cephei, the H-alpha is the only indicator of the presence of an accretion disk around the B star, and all other spectral lines are seen here are from the M2 supergiant. Yeah, I recorded this first spectrum with a small Maksutov spectrograph, is seen here in the picture below, in July 1996. This figure here shows my current slit spectrograph, the L-Hirus 3, which is mounted here on the Schmidt-Kassegan telescope C14 in the observatory of the Cologne Astronomical Association, of which I'm a member. And in 2015, a photometric and spectroscopy campaign was organized by Jeff Hopkins, by Philip Bennett and myself to monitor the eclipse of 2017 to 19, which began around the beginning of the August 2017 and lasted approximately 650 days. And with high-resolution spectrograph, such as L-Hirus 3, for instance, we can study now the dynamics and the accretion region around the companion, around the B star, which are responsible for the recombination spectrum in the H-alpha emission. And this is done in the visible spectral range by measuring the equivalent width and the maximum line flux, as well as by measuring the radial velocity. The radial velocity of two components, the blue component, the V component, and the other component, the R, the red component. And this figure here shows a section of 6,520 angstrom to 6,610 angstrom, the typical spectral range of the H-alpha double emission peak in CCD spectra. And lower resolution spectra, such as with LP600, for instance, will not provide useful measurements of the equivalent width, of the line profile, even of the radial velocity. However, it does have the advantage of providing useful spectral photometric information about the entire radiation flux by imaging the entire visible spectral range at short exposure times. That's one of the advantages. And here we see the long-term monitoring of the H-alpha equivalent width, which has been carried on for 25 years from July 1996 until today, whereby the 1997 to 1999 eclipse of the B star and its accretion region could be very nice observed. And since April 2010, a number of the observers of the Ernst Spectroscopy group have been involved, meanwhile, in this long-term monitoring. And this monitoring here shows notable long-term and short-term fluctuations in the H-alpha emission outside of the two eclipse processes. The slow variation apparently correlate with the orbital separation of these both components, of these both stars, and also an increased emission flux was observed when the B star was near the periastron. In all phases of the eclipse, we could observe a cyclic short-term variability of the H-alpha equivalent width, which was completely unknown in VBSEP and especially noticeable during the phase or in the phase of the total phase. It was totally unknown until our observations. And this cyclic variability thus made it also difficult to determine accurately the contact times, which is why the contact time T1 cannot be given reliably here. And the previously continuous high observation density, even before the actual eclipse, plus the spectral resolution of the spectrographs used here in this campaign, allows now a detailed analysis of the red-shifted component of the H-alpha emission, which is denoted here by R, and the blue-shifted component, which is here denoted by V. And this figure here shows for both emission components during the entire eclipse process, the relative line flux on the left ordinate and on the right ordinate the equivalent width. And this plot shows here also that even during the phase of the total eclipse, where the direct view into of the accretion disk is prevented, a quasi-periodic variations of both parameters can still be seen. And the difference in emission at the beginning of the process, as well as the fact that emissions persist throughout the eclipse, but above all, the difference at the end of the eclipse, at the end of the eclipse implies that both emissions must come from an extended, physically different, totally different area beyond the accretion disk. In almost 1,000 spectra, results of the period analysis of the equivalences of the line and of the line flux of both components, as well as the phase diagrams, indicate a significant period of approximately 43 days. And this 43-day period is shown here in this figure on the left side as the equivalent width, as well as the relative line flux of the right side of both emission components. And the significantly narrow profile shape of the H-alpha emission during the total eclipse, the profile during the total eclipse, seen here as a red curve, implies a lower velocity source far from the accretion disk, confirming that not all of the H-alpha emission come from the accretion disk. It's important. The model that emerged from this consideration is that of, let's say, two emission lobes rising above and rising below the orbital plane, with a limited region of a narrow waist, let's say, a narrow waist of emission in the orbital plane surrounding the immediate vicinity of the hot star, the companion, and its accretion, associated accretion disk. And these two emission beams, which propagate above and below the orbital plane, must be regions, of course, of ionized hydrogen maintained by photoionization of the far ultraviolet radiation emitted by the hot star, as well as by the equally hot accretion disk around this surrounds this star. And the ionizing ultraviolet radiation is directed in two, let's say, spotlight-like beams into the circumstellar gas above and below the orbital plane, where the gas density is much lower than in the orbital plane, which absorbs denser gas in the orbital plane onto the disk. In this model here, the redshifted emission, the R emission, come from the lower lobe, which is slightly inclined towards the observer's line, while the blue shifted emission, the V emission, comes from the upper lobe, which is slightly inclined far away from the observer. And in addition, the blue emission lobe, the V lobe, must be tilted slightly closer to the M star at the start of the eclipse, whereas the R lobe, the red emission lobe, must be slightly more distant to account the asymmetric nature of the V over R curves we saw before. So, if you assume that the rotation axis of the accretion disk around the B star precedes periodically, then varying surface portions of the upper emission lobe V and the lower emission lobe would produce the observed variability of the equivalent width and the line flux in the observer line of sight. And if this model were correct, then the precision of the disk rotation axis with a 43-day period that continues in both emission lobes would be the same for both sources. However, this would mean that the equivalent width and line flux amplitudes of both sources would necessarily be larger before and after the eclipse than during the eclipse. We can see here in this figure that is indeed the case, that it is clearly to see that the amplitudes of the equivalent width on the left side and the amplitude of the line flux on the right side of both emission components before, during, and after the eclipse. Yes, I would like to use the pointer. Yes, the amplitudes of the equivalent width before the eclipse, during the eclipse, and afterwards. Here's the same. It was for the V component. Here we have the equivalent width of the red component before the eclipse, the phase of the total eclipse, and the phase afterwards. The same we can observe for the V component, for the blue emission component before the eclipse, during, and afterwards, and here for the red emission component before, during, and afterwards. And this figure here shows also the phase dispersion minimization period analysis of the V over ratio. Now let's see before another state. According to the equivalent width and the flux ratio periodicity of both components, we of course we have to expect a corresponding periodicity of the ratio of the flux ratio of these both components. That should be also to expect. And this figure here below shows the period analysis of this V over R ratio of all data in the upper plot and correspondingly in the phase diagrams below. And this analysis here impressively confirms the real periodicity of both single emission components. In the model presented here, elaboration of the B star accretion disk as a consequence of the precession of its rotational axis is assumed as a cause of the periodic equivalent width and the line flux variability. And it seems highly unlikely that the pulsation of the M star produce such a regular density variation in its outer atmosphere that could explain this short 43-day period of the obscured disk. And the German astronomer Hummel suggested in 1998 that nodding vibrations, such as those occurring in the gas disk of B stars, could be induced by tidal effects by a companion star, with which the precision of the disk axis rotation could plausibly, in my opinion, explain the periodic V over R variation. But also the gravitational force of the M star exerts force torque on the B star disk that could trigger the 43-day precession period. But the period of only 43 days, could mean that the mass and the diameter of the accretion disk would also have to be correspondingly small. A precessing disk rotation axis with a period of 43 days would inevitably lead to a simultaneous variation of radial velocity of the line flux, at least of the V component. The first sign of a certain periodicity of the V component we already evident in the period analysis in the time behavior of the line flux and of the equivalent risk of this H-alpha component I showed before, based on 400 L-3 spectra from January 2018 to September 2019. It was now possible to carry out precise radial velocity measurements of the V component. And for this purpose, all spectra were recalibrated with so-called metal lines of the M star, the wavelengths of which are known very precisely from previous professional investigations or studies by the astronomer White. And due to the rather low mean radial velocity amplitude of 1.9 kilometers per second, this is not as easy as it initially seems. Despite the high velocity, the high accuracy in wavelength calibration in the order of 10⁻³ to 10⁻⁴ angstroms, the error in radial velocity of the radial velocity measurements in a single spectrum in one observation night is still in the range of 3 kilometers per second. That means this recalibration method results in a radial velocity which is to be understood as a relative velocity compared to the M star, a relative radial velocity to the M star without any influence of the system radial velocity. The upper plot here shows the radial velocity monitoring of this V component as black dots are smoothed by polynomial smooth by the red curve, and the detrended data as the blue dots. The middle plot shows eventually the PDM period analysis of the detrended data, and the bottom plot shows finally the phase diagram of the found period of, here let's say, 51 days. Yeah, unfortunately, this 51-day period doesn't fit at all to the precision period of 43 days. In spite of the high accuracy in wavelength calibration, the period of 51 days compared to the 43-day precision period of the disk rotational axis is not clear so far, sorry. Possible causes could be a superposition of the ultrasonic velocity, the ultrasonic orbital velocity of the B star. It could be also a superposition of the self-rotation of the M star and or its own pulsation period. In any case, the difference of 10 days of these two periods is reason enough to observe VB Cephei for the next 20 years. Thank you. Yeah, are there any questions? Anatoly.
Can we go back to your slide number 21? Yeah, here.
Oops.
The next
This one.
Yeah. So how did you determine that average curve, the red curve on the bottom plot?
How
did you get this red curve? Average.
Yeah,
So my question is actually, why didn't you draw it like this?
Yes, Anatoly, a simple answer. I used a special program which did not allow to create or design a fit which could be fit better within this curve distribution. But that is a limitation of the program I used.
I'm just wondering, maybe with other polynomial or other function, you
Yeah.
can get a better
Yes, yes, yes.
to
yes.
take into account this
Yeah.
lower point. If it tells us something about physics.
If yeah, it seems that is totally understood. Wonderful. Yeah, great. Thank you again.
Yeah.
Jack?
Yes, Jake.
Do we still need to keep monitoring it?
Yeah.
Sorry, a little bit louder.
Do we still need to keep monitoring?
Yes,
Gauge
yes, yes,
alpha-
yes, yes,
gauge
yes.
alpha line?
Yes, Jake, you have to know. After this eclipsing process, we were in the phase shortly before the periastron passage. But it would be high interesting to see how these different parameters we discussed here, how these parameters behave after the periastron passage. That could be a total different phase of the orbit of the total system. But again, the results we discussed here, or which I showed here, are only behavior of the different characters shortly before the periastron passage, and it would be highly interesting to see what happened afterwards.
What
Yeah.
is the cadence of the observations?
Oh, I would say once per month would be enough.
Okay.
Yeah, because the time from the periastron passage to the apastron, that's that's time enough. It's many years. Let's say around about 12 to 30 years.
But to get these periodically things also in the new observations, I think one per month is not enough for. So if you want to see this 51
Oh,
days,
yes,
or
you're right. But you're right. If we want to see what about the, particularly for the 43 period, precision period, yeah, of course, once per month would be surely too less. It's clear. Mm. But the question is how many colleagues or
Yeah.
observers from the amateur region or area would be willing to study this star again, yeah, we have to wait and see what will happen with the cadence of observations. Yeah, okay, thank you very much.
thank you.